Okay, let's talk about quantum particle distribution in a half-harmonic oscillator. Here's the problem we are looking at today. We have quantum particles each with a unit mass in a specific type of potential. The potential V of x is defined in a piecewise way. It's 1/2 omega squared x squared when x is greater than 0, but it's infinite when x is less than or equal to 0. These particles are in equilibrium at a temperature T. We are given that N2 and N3 represent the numbers of these particles found in the second and third excited states respectively. The question asks us to find the ratio N2 over N3. We are given 4 possible answers for this ratio. Option 1 is xp of the fraction 2 h bar omega over kBt. Option 2 is xp of the fraction h bar omega over kBt. Option 3 is xp of the fraction 3 h bar omega over kBt. And option 4 is xp of the fraction 4 h bar omega over kBp. So how do we approach this problem? We need to find the ratio of particle numbers in the second and third excited states for a system that's in thermal equilibrium at temperature T. To do this, we need to follow 2 main steps. First, we have to figure out the energy levels for this particular system, which is described by that potential. Second, once we have the energy levels, we'll use the well-known Boltzmann distribution to calculate the ratio N2 over N3. Let's dive into step 1, determining the energy levels. Remember, the potential V of x is 1/2 omega squared x squared for x greater than 0 and it's infinite for x less than or equal to 0. What this means is that for x greater than 0, it looks just like a standard one-dimensional harmonic oscillator potential. But the infinite potential for x less than or equal to 0 acts like an impenetrable wall right at x equals 0. The Schrödinger equation for x greater than 0 is given by minus h bar squared over 2m times d squared psi by dx squared plus 1/2 m omega squared x squared psi equals E psi. The problem states the particles have unit mass, so m equals 1. This simplifies the equation slightly to minus h bar squared over 2 times d squared psi by dx squared plus 1/2 omega squared x squared psi. Now let's continue with determining those energy levels. The infinite wall at x less than or equal to 0 is a crucial boundary condition. It forces the wave function psi to be 0 right at x equals 0, so psi of 0 must be 0. Let's think about the standard one-dimensional harmonic oscillator which exists from minus infinity to plus infinity. Its energy eigenvalues are given by En equals open parentheses, n plus 1/2 close parentheses, h bar omega, where n can be 0, 1, 2 and so on. The wave functions for this full harmonic oscillator psi n of x are either even functions of x when n is even or odd functions of x when n is odd. The boundary condition we have psi of 0 equals 0 means that only the wave functions that are odd with respect to x are allowed. The allowed eigenfunctions for our half-harmonic oscillator are the odd eigenfunctions of the full harmonic oscillator, corresponding to n values 1, 3, 5 and so on from the full oscillator spectrum. We define a new quantum number, k, specifically for the states of our half-harmonic oscillator, starting k from 0 for the ground state. As shown on the slide, the k equals 0 state corresponds to n equals 1 from the full oscillator. The k equals 1 state corresponds to n equals 3. The k equals 2 state corresponds to n equals 5. And the k equals 3 state corresponds to n equals 7. The slide also shows the corresponding energy levels for these states. In general, you can see a pattern. The energy for the kth state is given by the formula Ek, shown here on the slide, expressed in terms of k. Now we move to step 2, applying the Boltzmann distribution. When a system is in thermal equilibrium at temperature T, the number of particles, Ni, in a state with energy Ei is proportional to the Boltzmann factor, which is e to the power of minus Ei divided by kBt. For the second excited state, which is k equals 2 and has energy E2, the number of particles, N2, is proportional to e to the power of minus E2 divided by kBt. For the third excited state, k equals 3, with energy E3, the number of particles, N3, is proportional to e to the power of minus E3 divided by kBt. The ratio N2 over N3 is then given by the ratio of these Boltzmann factors, e to the power of minus E2 divided by kBt, divided by e to the power of minus E3 divided by e to the power of minus E3 divided by kBt. Using properties of exponents, this simplifies to e to the power of minus open parentheses, E2 minus E3 close parenthesis divided by kBt, which is the same as e to the power of open parenthesis, E3 minus E2 divided by kBt. So we need to calculate the energy difference, E3 minus E2. From our work in step 1, we found E2 is 11 halves h bar omega and E3 is 15 halves h bar omega. Let's calculate the difference. E3 minus E2 is 15 halves h bar omega minus 11 halves h bar omega. This equals open parenthesis 50 minus 11 close parenthesis over 2 times h bar omega, which is 4 over 2 h bar omega. And that simplifies nicely as this t minus h bar omega, which is 4 over 2 h bar omega. Now for step 4, we substitute this energy difference into our ratio formula. The ratio N2 over N3 is e to the power of open parenthesis, E3 minus E2 close parenthesis divided by kBt. Substituting our energy difference, this becomes e to the power of 2h bar omega divided by kBt. We can also write this using the exponential function notation as xp of the fraction 2h bar omega over kBt. Finally, step 5, let's compare our result with the options we were given. Our calculated ratio is ESP of the fraction 2h bar omega over kBt. Looking back at the options, 1 xp of the fraction 2h bar omega over kBt, 2 xp of the fraction h bar omega over kBt, 3 xp of the fraction 3h bar omega over kBt, 4 xp of the fraction 4h bar omega over kBt. In conclusion, by finding the energy levels for the half-harmonic oscillator and applying the Boltzmann distribution, we determined that the ratio N2 over N3 is xp of the fraction 2h bar omega over kBt. So the final answer is option 1.